All right, now that we've finished at least the basics of the differential calculus unit, we're going to start with integral calculus. And for now, just taking a look at basic, simple, indefinite integrals. Indefinite meaning we don't have boundaries defined, which you'll find out about in the future. Remember taking derivatives, you guys got quite good at this. Taking the derivative of this expression here gave us 2x minus 3. I had to restart this. The same here, 2x minus 3. The derivative of both of these would have been the same, which will tell us something special about integrals that we have to be careful with when we're working with indefinite integrals. You also were able to find the derivatives of these special functions like sine of x. The derivative of that was cosine of x, and the derivative of e to the x is e to the x, and the derivative of ln of x is 1 over x. These were all in your formula booklets. And when we move to integral calculus, we're actually just undoing, it's the inverse operation of finding the derivative. So we're asking ourselves, well, what function has this as its derivative? And so it's really working backwards. So whereas in these power laws, you did take the exponent times the coefficient, which weren't great to actually see in these examples, and then take one away from the exponent, we're going to first add 1 to the exponent and divide by the new exponent. But I think you guys are probably pretty good at doing this and can probably identify that this x squared would have the derivative of 2x. And what has the derivative of minus 3? Well, minus 3x, it's the same here. But what we need to be careful of is we actually don't know what constant there might be. So it could be plus some constant. Of course, it could be 0, but it could be anything else. So when you have this indefinite integral, this is the sign, it kind of stands for the sum, like a big S. It is indicating to undo it. You'll notice this notation is formed by both this integrand. That's the sign that kind of tells us about that we're taking the indefinite, that we're taking the integral, that we're finding the antiderivative, some might call it. And this means with respect to x. Especially at standard level, that won't really matter at all. It's almost just part of the notation for you. I mean, it's not really. I'll get into more of what it means in a couple lessons when we look at definite integrals, and then in higher level, it'll become more and more important to understand that that's not just a notation. But for now, it's okay to think of it like that. We have these two pieces, and inside is what we're trying to find the antiderivative of. Be really careful when you're looking at these trigonometric functions that you're watching the signs, because of course, as you take the derivative, the signs change in one direction. As you're going in the opposite directions, the signs will do the opposite. So what has the derivative negative cosine? Well, it's negative sine of x, because sine of x's derivative is cosine. So negative sine of x is negative cosine. Be really careful, because we learned with the derivatives, of course, the derivative of cosine is negative sine. But we're looking at the antiderivatives here. What has the derivative of e to the x? Well, e to the x does. And what has the derivative of 1 over x? Kind of just ln of x, but we have to be really careful because we can't have a negative value inside of ln of x. So if we were going down and we're given ln of x, it's easy enough to find the derivative, but we need to make sure that if we're looking at it this way, that this is the absolute value sign. It would have been given to us in the original function that we wouldn't be able to have a negative or a 0 there. Okay, of course we can't have 0 here anyway, but do be quite careful. These are all in your formula booklets, also in the other direction. So for these special functions, just look in your formula booklet if you're not sure or want to check something. Then of course we have maybe plus some constant, but we do need to include that here. At the end of this video, I'm going to have a few more for higher level that are also in the formula booklet. Okay. Here are some of the formulas. These are all in your formula booklet. You can see them here. I just said you could take a look and refer to them. These are not, but I mean, this is really just an application of that. Some constant is going to be like if you had the antiderivative of 3 dx, it would be 3x. We saw that, plus some constant. These are just some simple laws that work the same as if you had a derivative. Just like if you had the derivative of 2x squared plus 3x, you'd find the derivative of each piece. That's the same with integrals. You can either think of it as one antiderivative and separate it out into these two different expressions as well, with plus or minus. And you can also pull out coefficients. So if you had the antiderivative of 3x squared, you could say, well, it's 3, and I need to find the antiderivative of x squared dx. So that's also possible, just like when you were doing the derivatives. You do need to be quite careful with coefficients. Okay, you could think of this one, like we just said, as pulling the coefficient out. What's the antiderivative of e to the x with respect to x? Well, that's 3, and now we look at this, 3e to the x plus c. Slightly different here, and when it's in that function, you do need to check your work and just make sure you're considering, like, if I were to take the derivative of this, remembering the chain rule, am I going to get what I was originally working with? So if you say, well, the antiderivative of e to something is e to the something, okay, easy enough, but do remember, if you were to take the derivative of this, you would have to multiply it by the chain. So this isn't a 3 coefficient that we can pull out. It's not outside of the function here, really. It's inside and almost is working as a chain rule here. I mean, it really is. For the next lesson, you're going to find a more formal way of doing this, but we're just going to inspect it and say, well, I would need to multiply it by 3 after. So to make sure that's accounted for, I'm going to divide it by 3 or multiply by 1/3. So to check it, what you'd have to do is take the derivative. Well, 1/3 e to the 3x is 1/3 e to the 3x times 3, the chain, and that would give us the original thing, plus c. Same thing here. The antiderivative of negative cosine of something is negative sine of that thing. That's in the formula booklet. But there would be a chain here of multiplying by 2. So you do need to undo that so that if you were to recheck this and multiply back through, you'd get the 1 that's there. I'm going to add c, of course, as well. Okay. And then the same thing here. This looks a little bit funky. You could just say, well, I'm going to pull out the 3 and deal with that after and say this is 1/2x plus 1 dx. And what has this kind of derivative? If you look in your formula booklet, 1 over something is actually the ln of the thing. So I'm going to start writing here 3 times ln, absolute value of this. But you do need to make sure that you pull out this half here. Because if you were to recheck it with the derivative, you'd multiply by the 2. So you need to make sure that when you complete the derivative, you're going to get this original function. It doesn't matter. I mean, it wouldn't be applicable here either, but if you are thinking of yourself, like, do I do it to the c as well? It really doesn't matter because that c is an unknown constant regardless at this point. So our final answer, I could have left it till the very end, the c, because it really is meaningless until the end when we say we have our answer. It's just representing the possibility of something being there as well. So there are a few slightly trickier antiderivatives. Sometimes they may give you a point on the original function so you can find out what c is. Because remember, the derivative just gives you the gradient of something. But if you were to find the antiderivative, you don't know how far up or down that curve is. You just know the gradient, where it's going. So if the gradient, this derivative, is f prime of x, is 6x squared plus 4x minus 3, we want to find f of x. Well, that's the antiderivative of f prime of x. If you were to go up further and take the antiderivative of this, of f, you could call that like a capital F. That's a very common notation with respect to x. So these undo, the derivative and the integrand undo each other, the integrals, so we will get the f again. And what is the antiderivative of 6x squared plus 4x minus 3 dx? Sometimes you'll see that in parentheses. We're just going to undo this power rule. What has the derivative of this? I'm going to add 1 to the exponent. I know it goes up. Divide by the new exponent. You could check it. 2x cubed's derivative is 6x squared plus 2x squared minus 3x plus c, potentially. Now, they gave us this information, that if I have x equals 1, I'll get out -5. So what you can do is use this to set up an equation and find out what c is. There, so I'm putting in this point that was given. And as you simplify it, 2 plus 2 minus 3. Excuse me. So 5 is equal to 1 plus c. So c is equal to 4. Oh, there we go, is c. So the original function is f of x equals, where did I write it? There we go. 2x cubed plus 2x squared minus 3x plus 4. Okay, you no longer need the c because you found out what it is. And this function does have a gradient of 6x squared plus 4x minus 3, the derivative, and it goes through the point 1, -5. Ooh, it goes through the point 1, 5. I'm just going to change this so that I have it correct here and I don't have to do it again. There. The last thing for higher level, standard level, you don't need to listen anymore. These are just a few more standard integrals. They are, as you see, given in your formula booklet. A little bit weird is that they, I guess it's not weird, they don't always give you the antiderivatives, but at that level you should understand that if this is the derivative of that, then taking the antiderivative of secant squared of x will give you tangent of x. So you can work backwards with these as well. We're going to use some of this information to find some kind of crazier integrals. Here are just a few examples using the higher level integrals that we have here. You could rewrite this as 2 ln of 3 times 3 to the x dx. You don't have to, but it may be easier to then see what this might be. That's here. So if I were to undo that, we have ln of 3 to the x dx will give us a to the x. So I have 2 still, and the antiderivative of that is 3 to the x plus c. Do not try to multiply 2 times 3 and say that's 6 to the x. That's not true. Remember, the order of operations says we would have to do 3 to the x first. Since we can't, you can't do the multiplication. Here's another example. You will sometimes see this dx in the numerator because, again, you could just rewrite this as, pull out the coefficient. That's 1 over 1 plus x squared dx. That's nothing to do with calculus. That's just simple algebra. Excuse me. And then looking for what this might be, if you take a look around, that's this. So -3, and that's arctangent of x plus c. And that's it.